Hello, we're Team 3 from Guadalajara and we're going to present our solution for the autonomous driving challenge.
There are 4 subsystems, each making up a node in ROS. The image publisher uses NVIDIA's ROS wrapper to read the camera using GStreamer and publish it using CVBridge. The lane processing node subscribes to this image and determines the center of the line and thus the offset to set center. It also determines if the robot is at an intersection. The sign processor uses an image classifier to determine the signs in the image and passes this information to the controller, which determines an output control speed.
For the lane processing, we apply a threshold over the grayscale image to binarize it and use region of interest masking, such as the only thing in view is the center line. And to know the x-coordinate, we average all the x-coordinates from the Hoff transform and then approximate it. And we also use a Kalman filter as a linear predictor for the center filtering. For the intersection detector, we simply report the number of lines seen in the image, and if the number is either too high or 0, we report it as an intersection.
Using the same Hoff transform that we use for lane detection, we can measure the amount of lines in the frame at any given time. Normal pieces of track tend to have a moderate amount of lines, while intersections tend to have either no lines or a lot of them. We therefore keep account of the lines in each frame, and every time we see 0 or more than 20 lines, we add one void to a variable, and every time we see a value in between, we subtract 1 from it. When this variable reaches a threshold value, we publish a boolean that represents whether the robot is at an intersection or not. This threshold value, as well as the maximum and minimum values of the variable, are tuned experimentally.
For the sign classification, first we change the format of our image to a 640 x 640 resolution. Then we train our YOLO V5 model so it can detect the road signs. The signs are classified based on the size of the boundary box. If the size of the box is too small or too large, the sign won't be detected. When the puzzlebot reaches an intersection, the last sign the robot saw is saved, so it can decide if it has to turn right, left, or go forward.
Regarding the controller, we have 2 modes: open loop mode, which occurs when the robot is at an intersection, and closed loop mode, which occurs when it isn't. Open loop mode will follow the instruction of the last seen sign, meaning the robot keeps a constant angular velocity related to the direction it has to go in, be it to keep moving forward or turn to the right or to the left. On closed loop mode, a control loop calculates both linear and angular velocity and outputs them as a twist message. Detections of signs and traffic lights, which affect velocity, are directly mapped to a velocity multiplier.
The angular velocity in line follower mode is a PID controller where the error is the offset of the robot to the center of the lane. This control is bound by a sigmoid function that helps the output velocity stay in a manageable range. The linear velocity is simply constant. Notice that both expressions are affected by a multiplier, which is determined by the sign present in the image. If it's green, the multiplier will be 1. If it's yellow or construction, it would be a float, meaning slowing down, or if it's stop or red, it will be 0, meaning stop.
These are the implementation challenges which I will walk through during the demo video. So we had some issues with the OpenCV installation which didn't have a CUDA compatibility, so we compiled a newer version and also for it to be compatible with YOLO V5 operators. Also we had some trouble with the processing resources from the Jetson. RAM was simply not enough, and we also had to run the classifier in C++ for it to be faster. And the vision robustness, we had to vary the lighting conditions and POV for the dataset. Also, we wrote a simple data collection script to ensure the same amount of samples was present for each class. And we also trained the YOLO V5 network with at least 200 epochs to ensure network convergence. Thank you for your attention.